Hello everyone, welcome to GE Math and welcome to another lesson video. This time it is going to be about the binomial series for rational powers, or we are extending the binomial theorem for rational powers. So it's not just about the powers which are integral or integers, but we are going to have also powers or indices of the binomial which are fractions, decimals, or even negative numbers. Now, for us to understand the existence of this concept, let's try to recall first the binomial theorem that we learned, that is for any positive integer n, specifically this 1 plus x to the power of n, where n is a positive integer. So the expansion, as we know, is will be like this: 1 plus nx plus combination of n taken 2x squared plus combination of n taken 3x cubed up to the last term x to the power of n. Now we can also rewrite this using the definition of combination, wherein combination of n taken 2 is simplified to be n times n minus 1 over 2, and n taken 3 is n times n minus 1 times n minus 2 over 3 factorial. In the same manner, if our second term is negative x, we can rewrite, or we can write the expansion in this form. Now, another thing that we need to remember is this one: 1 minus x plus x squared minus x cubed plus infinity. So recall that this is actually what? This is an infinite series. Now, specifically, this is an infinite geometric series, and we know that the common ratio is negative x. So our R common ratio is equal to negative x. So using now the formula for the infinite geometric series, wherein the formula is the first term divided by 1 minus the common ratio. So in this particular series, our first term is 1. That's why this is 1. And 1 minus negative x, which will be 1 plus x. So now this is the formula, or this is the algebraic expression that is equal to this infinite geometric series. Now, there is a condition for this to exist. Okay, if you remember, this one needs to converge. For this to have a finite sum, the common ratio must be between negative 1 to 1, or we can also put it in the symbol. The modulus of x must be less than 1, so that this infinite series will converge. Now, when we say converging series, it means it is approaching a particular number. So the sum is going to be something finite. All right. Now, we can also rewrite 1 over 1 plus x as 1 plus x to the power of negative 1. So you can now somehow see here that 1 plus x to the power of negative 1 is existing. So it is possible, but with a certain condition. And the condition is the modulus of x must be less than 1. Okay, so it also follows that 1 plus x to the power of n, where n is a rational number, can also exist. It is possible as long as the modulus of x is less than 1. So please remember this condition, that this binomial series, this binomial expansion, wherein the power is something rational, can only exist. It's only possible if the modulus of x is less than 1, meaning it should be between negative 1 to positive 1. So now we have somewhat established the possibility or the existence of the expansion of 1 plus x to the power of n, where n is any rational number. But as long as your modulus of x, the second term here, is less than 1. Now let's take a look at a particular example. What do you think will happen? Of course, we're going to use again the formula. So let's try to expand 1 plus x to the power of negative 2. So this will be equal to 1, and then this will be equal to 1. Then n is negative 2, so this is minus 2x. And then n taken 2 here will become negative 2 taken 2x squared Similarly, n taken 3 will become negative 2 taken 3 x cubed. Now, if we're going to continue the coefficients, so the next coefficient will be negative 2 taken 4, followed by negative 2 taken 5, then followed by negative 2 taken 6, negative 2 taken 7. So what do you think will happen? So what do you notice? It's going to continue on and on. It's not going to stop because the value of r is not going to be equal to the value of n. So it will continue uh, infinitely because we will never reach negative 2 taken negative 2. So that's why this is going to be an infinitely long polynomial. So this is going to be an infinite series, right? Now, another thing is if you're going to use an ordinary scientific calculator, negative 2 taken 2 is what? If you try to input this in your scientific calculator, you won't get an answer. It's going to be a math error. But if you're going to use a graphic display calculator just like the TI Inspire CX, okay, let's try. So the question is, what is the value of combination of negative 2 taken 2? So let's use this one. We are on our calculator page. We go to menu and then scroll it down and then go to number 5, which is probability, and then go to number 3, which is combinations. All right, now we input negative 2 taken 2, so this is going to be negative 2 then comma 2. Okay, so as you can see, the answer is equal to 3. To make sense of it, let's use the definition of the combination of n taken r. It is equal to n factorial divided by n minus r times n minus r factorial times r factorial. Okay, so what we can do is we can rewrite this so that it can work for rational numbers, so that we can get the value using the formula of, let's say for example, combination of negative 2 taken 2, which we found to be equal to 3 using the GDC. Okay, so how are we going to rewrite this? Now, take note that n minus r factorial here, the one in the denominator, can be equal to n minus r times n minus r minus 1. And then the next factor will be n minus r minus 1 minus 1. So you just have to keep on subtracting 1 until you reach 1 here. Okay, so that is the definition of n minus r factorial. So that is basically from the definition of factorial. Okay, so let's expand this. N factorial is actually n times n minus 1 times n minus 2. Now, since our n, we want this to be a rational number, you can actually reach a point wherein there will be a factor that will be before n minus r factorial, and that's going to be n minus r plus 1, right? So you will be able to reach this, okay? And then of course, if we keep subtracting 1, n minus r plus 1 minus 1, the next factor will be n minus r, then followed by n minus r minus 1 until you reach 1. Okay, but notice that n minus r times n minus r minus 1 up to 1 is actually n minus 1, n minus r factorial. So that means we can actually cancel that out. Okay, so what remains is n times n minus 1 times n minus 2 up to n minus r plus 1 divided by r factorial. So, which means we have now rewritten our combination of n taken r, and this is now going to be applicable, or this can work for n for n rational numbers. Okay, so let's take a look at this example. N taken 2. What is n taken 2? N taken 2 is, we know that it is n times n minus 1 over 2 factorial. So using this formula, what is n minus r plus 1? N minus r plus 1, our r is actually 2, right? So n minus r plus 1, it's going to be equal to n minus 2 plus 1, and that is simplified to n minus 1. What does it mean by having this? It means, okay, it means that you have to stop at n minus 1. So you begin at n, and then you have to stop at n minus 1, then all over 2 factorial, which is correct, right? So this n minus 1 is actually this. Now let's try that for n taken 3. We know that n taken 3 is n times n minus 1 times n minus 2 over 3 factorial. Now, so if you use this formula, we have to stop at n minus r plus 1. So for this n taken 3, what is our n minus r plus 1? R is actually 3. So n minus 3 plus 1, negative 3 plus 1 is n minus 2. So that means we have to stop at n minus 2. So you just have to start from n, then keep subtracting 1, and then you have to stop at n minus r plus 1. So if we're going to use this definition uh, to expand, let's say for example n taken 4, then you have to stop at n minus 4 plus 1, which is going to be n minus 3. Okay, so now we can use this formula now of the new, is like the new formula for the combination to evaluate n taken r, where n is a rational number. Okay, so let's try this example. What now is negative 2 taken 2? So using this formula, okay, using this formula, because this is now our n taken 2, this is our n taken 3, so which means n is negative 2, so this is going to be negative 2x, right? And then n times n minus 1 is going to be negative 2 times negative 2 minus 1 over 2. Whereas the other one, the next term is n times n minus 1, n minus 2 over 3 factorial. It's going to be like this, where n is equal to negative 2, right? So earlier we used GDC to evaluate negative 2 taken 2. And if you're going to simplify this, negative 2 times negative 3 is going to be positive 6 divided by 2, and that is equal to positive 3, right? So, and this one is going to be negative 4. So this is now the expanded form of 1 plus x to the power of negative 2, and that is going to be infinite, all right? Infinite series. And we have to make sure that we have to write that this one can only exist, this is only valid if our modulus of x is less than 1. Alright, so these are the 4 terms in ascending powers of x. And of course, you can continue that using this combination formula and using the definition of the expansion. Alright, so the big concept now is, again, if the modulus of x is less than 1, then for any n is a rational number, we have this expansion. Okay, and this will be an infinite series. Alright, now let's go to the second example. How do you expand now 1 over 1 plus 2x to the power of 2? You know that you can rewrite this . Alright, so it's time for our second example, 1 over 1 plus 2x to the power of 2. So the questions are: expand up to the term in the x cube and state the values for which this expansion is valid. And then we have to use the result from A to estimate 1 over 1.06 to the power of 2 correct to 4 decimal places. So let's answer first letter A, and that is to expand it. Okay, so using the formula, so we're in, this can actually be written as 1 plus 2x to the power of negative 2. So again, our n is equal to negative 2, but take a look at our second term. This time it's no longer x, but it is 2x. Okay, so using the formula, just plug in n, which is equal to negative 2 in our x in the previous example, or in the formula, it's going to be now 2x. Alright, so up to the x cube term, so that means we have to stop here. Alright, so simplifying that accurately, and then it will give us 1 minus 4x plus 12x squared minus 32x cubed. Now, let's look at, let's answer this question, state the values for which the expansion is valid. So remember that this can only be possible for a certain condition of the second term. And this time, it's going to be the modulus of 2x that should be less than 1. Okay? Now, let's simplify this further. okay, in such a way that it will end up with the modulus of x that must be less than a specific number. Okay, so let's recall the meaning of modulus of 2x that is less than 1. It's actually 2x that is more than negative 1, but less than 1. So it is defined to be like this, okay, if we can still remember. And then we can simplify this in such a way that we can divide the whole inequality by 2, and it will result to negative 1 half less than x less than 1 half, or x is more than negative half but less than half. And then we can write this back to an inequality with modulus, or modulus inequality, and that will be modulus of x is less than 1 half. So the expansion, the infinite series, is only valid if our x is between negative half and 1 half, or modulus of x is less than 1 half. All right, so this is our expansion. Make sure that you write this expression, this statement, that it is only valid for this particular values of x. Okay, so now let's use the result in B to estimate this number correct to 4 decimal places. Okay, so compare now this. So 1 is the same, 2 is the same, therefore 1 plus 2x must be equal to 1.0006, or we can also infer from that that 2x is equal to 0.06. Solving for x, that will be 0.03. So this time we can substitute the value of x, 0.03, in this expansion. And we are going to have 1 minus 4 times 0.03, and then we can get now the value, and that is 0.8899. This is correct to 4 decimal places. Okay, now let's proceed to the third example, and that is square root of 1 minus x. So it's the same thing. We have to expand this up to the term in x cubed, and I think we need to rewrite this in such a way that it's going to be quantity minus x to the power of 1 half. Okay, so once again, let's use this formula. So this time our n is 1 half and our second term is negative x. Okay, so we will now have 1 plus n. Notice that this is 1 half and then x is negative x. Okay, then follow the formula and then simplify this accurately. Find the values. So the 4 terms up to the x cube is 1 minus half x minus 1 over 8 x squared minus 1 over 16 x cubed. Okay, now let's answer the next part of the question, which is state the values for which the expansion is valid. So what you can do is look at the second term, get the second term, put it under the modulus symbol. That will look like this, and it should be less than 1. So modulus of negative x is less than 1. Simplify this further. So you can remove the modulus symbol, and the definition is x is more than negative 1 but less than 1. Rather, negative x is more than negative 1 and less than 1. So let's remove the negative symbol there. So what you can do is divide the whole inequality by negative 1. And you know that when you divide the whole inequality by negative 1 divided by negative 1 will become positive 1. But the symbol will reverse. So instead of a less than here, will become greater than. So in short, it will look like this. But it is more proper to write our inequality just like this, wherein the smaller number is at the left and then the bigger number is at the right. Okay, so follow the number line. So this is also the same as negative 1, or x is more than negative 1 but less than 1. So in short, this one is also the same as the modulus of x is less than 1. So our expansion therefore is valid for modulus of x is less than 1. It is always better to write, to simplify this statement, wherein the only expression inside the modulus symbol is x. Okay, all right, now let's go to the second part, or the B question, which is let's use the result from A to estimate the square root of 24 to 4 decimal places. Now the thing here is if you rewrite square root of 24 following this 1 minus x as 1 minus negative 23. Okay, but the thing is, the condition from A, our modulus of x must be less than 1. So looking at this, if you follow this, it's not going to satisfy the condition because negative 23 is outside of the range from negative 1 up to 1. So we have to manipulate this square root of 24. We have to represent that in another form in such a way that our x must be between negative 1 to 1. Okay, so what can be done here? So square root of 24 can be written as square root of 25 times 0.96. So we thought of a perfect square, okay, because later on a perfect square can be simplified and can be taken out of the square root sign, right? So what I did was we can divide the square root of 24 by a perfect square, okay, and that will be square root of 25, so that we can get a very small number as a quotient of it, and that is 0.96. So square root of 24 here, square root of 25 times 0.96. Simplify this further, it becomes 5 times square root of 0.96, and we know that 0.96 can be written as 1 minus 0.04. So obviously here, this follows now the pattern of square root of 1 minus x. And the x here being equal to 0.04 is now within the condition that is between negative 1 to 1, right? So therefore, we can now use this for us to estimate the value of square root of 24, all right? So we will use the expansion, which is the result from A, to get the value of square root of 1 minus 0.04. So we will have 5 times the quantity, okay, 1 minus 1 half times 0.04 minus 1 over 8 times 0.04 square minus 1 over 16 times 0.04 to the power of 3. All right. Okay, so that means, okay, so let's use now our calculator to get this, and in 4 decimal places, it is going to be 4.8990. Now, what you can do is you can also get the square root of 24. You can directly get the answer of that just to compare if our answer is a close approximate value, a close estimate to the actual answer from our calculator. All right. Okay, now let's go to example number 4. Example number 4 is, okay, expand up to the term in x cubed and state the values for which the expansion is valid. Now we can rewrite this as 4 plus x to the power of negative 1 half. But the formula is 1 plus x to the power of n, okay, where n is a rational number. The problem with this is the first term is a 4 and not a 1. But what we can do is, again, we can simplify or manipulate in such a way that the first term is a 1. So for us to be able to do that, we can bring out the 4, okay, and it will look like this. 4 times 1 plus x over 4. So this one is equivalent to 4 plus x, right? And the whole thing will be raised to the power of negative half. Okay, now use the law of use the law of indices to simplify this further. So 4 to the power of negative half is actually 1 half, and then 1 plus x over 4 to the power of negative 1 half. So this is now what we can expand, okay, using the formula. So alright, so we're in our n is negative 1 half, and the second term is x over 4. Alright, so just be careful with this. Don't commit some careless mistakes here. Okay, so and then take note that 1 half should be outside and to be multiplied to the whole expansion. So don't forget this outside factor 1 half. Okay, so this is now 1 half times 1 minus 1 8x plus 3 over 128x squared minus 5 over 1024x cubed. And then you just distribute 1 half inside. Okay, and this is now the expansion of 1 over square root of 4 plus x only up to the x cubed term. We know that this is going to be an infinite series, but we only stop at the x cubed term. Okay, now valid for what? Okay, valid for what? So what you can do is take a look at the binomial expansion that we expanded actually. So 1 plus x over 4 to the power of negative 1 half. So this x over 4, which is the modulus of x over 4, must be less than 1. Okay, so if you, again, you remember, if you're going to remove the modulus symbol, it's going to be x over 4 more than negative 1 but less than 1. So if you try to remove the denominator 4, then you can just simply multiply the whole inequality by 4, and you will end up with x is more than negative 4 but less than 4. And you can write it back with the modulus symbol as modulus of x less than 4. Okay, so there's actually a shortcut here. If you look at x over 4, the coefficient here is 1 over 4. So you just get the reciprocal of that, which is 4, and then you will have already the statement for which the binomial expansion is valid. Okay, so that's it for today, everybody. Okay, so thank you very much and see you next time. Bye bye.